Welcome friends. So in the last lecture we have discussed insulators, equivalent circuit of insulator assembly, whether or suspension type insulator assembly, and thereafter we have seen the voltage distribution along the various discs are not uniform. So to measure the uniformity in the voltage distribution, we have defined a term called string efficiency. There we have seen if the string efficiency is say 70%, that means 70% is the uniformly voltage is distributed and rest 30% is non-uniform. From there we have seen that if voltages are made closer to each other, then string efficiency can be improved. Now in this class we shall see different problems and the method of improvement of the string efficiency. Now in order to improve the string efficiency, because we need to improve the efficiency because voltage distribution are never same. Voltage distribution are never uniform. So we need to have we need to have it near to 100% or at least near to 90%. So the solution is by adding a guard ring. It is a special arrangement. It's like a ring like structure which is installed in the tower and insulator assembly junction between the insulator and tower assembly. So by placing that guard ring, voltage distribution can be made more uniform. Hence, of course, if this can be made more uniform, then string efficiency will automatically improve. What it does actually, this guard ring it introduces another set of capacitor. Which will inject some currents that will neutralize either partially or fully the current flowing to the shunt capacitance. And that means if this is the structure of the insulator assembly, I am roughly showing this is the conductor. So guard ring is placed at this point, so it is basically a ring like structure. So it will essentially provide a capacitor like this, a new set of these capacitors. Now this current, let us say this is I1 and let us say this is I1 dash. So this I1 and I1 dash either same or that means this I1 dash either fully neutralize I1 or partially neutralize I1, so that this voltage distribution can be made more uniform, because voltage is only non-uniform because of this current flowing through the shunt capacitance, this small I1, small I2. So only if this small I1, small I2, small I3 currents can be partially removed or totally removed, then only the current flowing through the series capacitors are same, and hence voltage drop is same and this voltage distributions are same. So one way you can think to partially neutralize or fully neutralize, to introduce a new set of capacitor like this, which can be done by providing a guard ring. Another thing can be obtained by using a larger cross arm. That means this length should be more. But it is not an economical solution, so it is not achieved in practice. So now let us solve one or two problems and see by involving this guard ring, or by introducing this guard ring, how the string efficiency can be improved. So let us straight away we have come with a problem, that is we have a 4 unit. As it can be seen. Now we have m is equal to 0.12. Now you need to evaluate string efficiency. Now the solution is So string efficiency is the voltage across the disk, that is V1 plus V2 plus V3 plus V4, and now divided by N, that means number of disks, that is 4. Now voltage nearest to the conductor, it is V4, and then it must be multiplied by 100% to get the string efficiency. So as you know, V1 is V1 and V2 is 1 plus M into V2, 1 plus M into V1. V3 you know 1 plus 3M plus M square into V1, plus V4 is 1 plus 6M plus 5M square plus M cube into V1, and in the denominator we have 4 into 1 plus 6M plus 5M square plus M cube into V1. So if you cancel out all M1, so it will be, now in the numerator we have 4 plus 10M plus 6M square plus M cube, and in the denominator we have into this term 1 plus 6M plus 5M square plus M cube. Of course you should multiply it with 100%. Now if you put M is equal to 0.12 in this expression, you will get numerator as 5.288, denominator as 7.175. It should be multiplied with 100%, and it is equal to 73.7%. 73.7%. That is the answer for string efficiency. This is the answer. So let us move forward to our next problem. Now this is a guard ring facility. So we have N is equal to 3 here. We have N is equal to 3 and M is equal to 0.2. So these capacitances are 0.2 C. Now evaluate string efficiency without guard ring and with guard ring arrangement. So let us first solve what is string efficiency without braiding ring or guard ring, whatever. So we have N is equal to 3, so we can write string efficiency is equal to V1 plus V2 plus V3 divided by 3 into V3. So you know V1 is equal to V1 plus V2 is equal to 1 plus M V1 plus 1 plus 3M plus M square into V1 divided by 3 into 1 plus 3M plus M square into V1. Now if you just put M is equal to 0.2, so the answer should be, the numerator will be 3.84, denominator should be 3 into 1.64, it should be is equal to 78%. Of course, you need to multiply it with 100. So without guard ring or braiding ring, my string efficiency is 78%. Now let us evaluate what will be the string efficiency if guard ring facilities involved or introduced. So problem part 2, with guard ring facility. With grading ring. Now the moment the grading is in, so these equations will not work. Because this current will be some value, will give some value, so those equations will not work. So in order to do that, let us solve. Let us say this is I3, capital I3. This current is capital I2 and this current is capital I1. Let us say this node is X, then this node is Y, and this current is small I2, and the current flowing through this newly introduced section is I2 dash, and the current flowing through this shunt capacitance is I1, and current flowing through this newly introduced section is I1 dash. So at node X, we can apply KCL. What is that? You see, at node X, this I2 and I1 dash, these two currents are entering, and the leaving currents are I1 plus capital I1. So what is I2? I2 is V2 into omega C. V2 into omega C. What is I1 dash? I1 dash will be nothing but V2 plus V3, V2 plus V3 into omega 0.15 C. Why? Because you see, I1 dash is this current, that means the potential drop between node X and conductor. So the potential drop between node X and conductor is V2 plus V3. So this is V1, this voltage is V2, and the rest is V3 up to conductor. So the potential difference between node X and conductor is V2 plus V3. So that is why potential difference is V2 plus V3. And omega, now these capacitances are 0.15 C. So that is why this term is coming. So what is small I1? Small I1 is equal to simple V1 into omega C. And lastly, what is capital I1? Capital I1 is the V1 into omega C. So I have done one mistake. This small I1 is this current, so it should be omega into 0.2 C. Omega into 0.2 C. So now if you solve or if you simplify this, you will get 1.15 V2 plus 0.15 V3 minus 1.2 V1, it should be is equal to 0. So if you simplify this and taking all the terms on the left hand side, so you will get, so you name it equation number 1. Now we will go for the next equation at node Y. What is there at node Y? So you see, at node Y we have I3 as incoming, then we have this I2 dash as incoming, then I2, capital I2 as outgoing, and small I2 as outgoing. So now what is capital I3? Capital I3 is equal to V3 into omega C. Small I2 dash, that means it should be V3 into omega 0.15 C. What is capital I2? What is capital I2? Capital I2 is nothing but V2 into omega c. And what will be small I2? Small I2 is nothing but V1 plus V2 into omega 0.2c. So again, if you simplify this above equation, you will get 1.15 V3, 1.15 V3 minus 1.2 V2 minus 0.2 V1, it should be is equal to 0. So it is equation number 2. So with these two equations, we need to get the final answer. How? So now from one, what we are getting, V2 is equal to 1.15 V3 V2 is equal to 1.2 V1, 1.2 V1. So this term is kept on the right hand side, then minus 0.15 V3 divided by 1.15. So it is equal to 1.04 V1 minus 0.13 V3. This is the V2 is equal to. From 2, we will have V2 is equal to 1. Sorry. It should be 1.15. It should be 1.15 V3 minus 0.2 V1 divided by 1.2, that will be equal to 0.95 V3 minus 0.16 V1. So now if you compare these two, V2 is equal to this and V2 is equal to this, so we can write (1.04 V1 minus 0.13 V3 is equal to 0.95 V3 minus 0.16 V1. So if you solve this, you will get V1 is equal to 0.89 V3. This is one relation we will require soon. Again, V2 is equal to 0.95 V3 minus 0.16 V1. 0.16 V1. So again, so V1 is what? V1 is 0.89 V3. So it will be coming out to be V2 is equal to 0.807 V3. So now we have string efficiency. It will be V1 plus V2 plus V3 by 3 into V3. So 0.89 V3, this relation. Then we should write this 0.807 V3. Then lastly we have V3 divided by 3 into V3. So if you solve this, you will get 89.9% as string efficiency. So what we have observed here, without string efficiency or without guard ring facility, the string efficiency was only 78%. But with guard ring facility, it's improved by some amount, and new efficiency is almost 90%. That means this much is voltage is uniform. The rest around 10% is non-uniform. So this is a clear indication that by improving or by introducing a grading ring or a ring-like structure like this, the string efficiency can be improved, or voltage distribution along the disc can be made more uniform. And next we have some few terms left, that is called arcing horn. What is arcing horn? The arcing horn essentially provides, you see, these are the insulator assemblies. You see, these portions are insulators assemblies, and you see this orange shaded region, these are, you see, these are called arcing horns. What is the purpose of this arcing horn? If some flashover comes or some high voltage trace has come, due to the presence of this arcing horn, a flashover can come or flashover can occur between these two arcing horns. So these insulators assemblies are kept shaped or kept shielded. Okay, these insulators assemblies are kept shielded from those electrical flashovers. So this is the purpose of arcing horn. And lastly, we have some testing to perform before installing into the actual field. Very few tests. First is power frequency dry flashover test. What is that? We have to apply AC voltage of 50 Hz, that is why it is called power frequency test, and it is increased at a uniform rate. Then at some point will come, that flashover will occur. If voltage is increased at a uniform rate, at some point will come, that insulator is along the insulator or across the insulator, a flashover will occur. So this performance or this test is called power frequency dry flashover test. Why dry? Because this test has been conducted in dry condition. The similar procedure is obtained during wet condition. The above procedure is repeated in wet condition. The artificial rain is created. What are the different conditions? It is the precipitation rate of 3 mm per minute. It should be directed along 45 degrees, so in this direction, and conductivity of the air being 100 microsiemens. Here at these three conditions, the artificial rain is created, and the same procedure has been applied to test the wet flashover test. And lastly, we need to have the impulse withstand voltage test. A standard impulse voltage wave is of both the polarities is applied to the insulator. What is impulse? Impulse is defined by this condition or this waveform. It's something like this structure. It is the peak voltage Vm, we have different times. Okay, we have T1 as wave front time, we have wave front time, we have T2 as wave tail time, different times. At a standard impulse wave is one which has got wave front time as 1.2 microsecond and wave tail time as 1.50 microsecond. A standard impulse wave is one which has wave front time as 1.2 microsecond and wave tail time as 50 microsecond. So this impulse wave of both the polarities is applied to the insulator. On application of 5 successive applications, if flashover does not occur, flashover or puncture does not occur, then insulator is passed the test. On the other hand, if two procedures or 2 out of the 5 applications, if 2 out of the 5 applications, 2 cases were found when the flashover or puncture occurred, then that insulator is failed. Then that insulator is rejected. Okay. So with this insulator chapter is ended here. So to briefly discuss, we have first seen what are the insulator, what are the main purpose of the insulators and various types of insulators, and thereafter we have seen voltage distribution along the disk of the insulator is not uniform. We need to make them uniform by providing appropriate arrangement. So string efficiency is defined accordingly, and it essentially measures the degree of similarity in the, or degree of uniformity in the voltage distribution along the disk. And later we have seen a ring-like structure is provided to improve the string efficiency, or rather to make voltage distribution more uniform. And we have solved 2 different problems of string efficiency. Later we have defined 3 different tests which is performed before installing an insulator. If I have an insulator, I am no one to install in practical field. It must be undergone several testing phases. Those testing phases, all the testing should be done appropriately, and that insulator piece of that insulator should pass all of those n number of tests. So then only it is allowed to install them in practical field. So with this, I am concluding here insulator chapter. So from the next class, we will start a new chapter. Thank you, and have patience hearing.